Okay. Okay, so today we'll go through the assignment 2, but there are only 5 questions in assignment 2 that will not take more than 12 to 15 minutes. So I thought that we can go through some examples of D'Alembert's principle or the Lagrangian equation. So today we will do some examples of those example and application of those principles. Okay, so as you know that you have done the D'Alembert's principle, and the D'Alembert's principle actually tells you Fi A minus Pi dot delta Ri is equals to 0, where this delta Ri is the virtual displacement. This Fi A, this A denotes it is the applied force, not the constant force, right? This is the applied force, not the constant force, and this Pi is the force or change of momentum. Okay, so this is the D'Alembert's principle, as you all know. Now we will apply this principle in various systems. Okay, now let us first take a triangular system. This is the this is the system, and two masses are there, and it is connected by a string. Okay, so this is the string. This mass is m1, this is m2. This is massless, this has no mass, and this string is actually a smooth and incompressible string. That means incompressible or inextensible, whatever you can say. So there will be no compression or extension of this particular string. Now there is only one external force that is acting on this system, that is the gravitational force, which acts along the negative z direction. Okay, so it is the negative z direction. So what are the force acting on this system? On this m1 mass, the downward force is m1g, and this on this m2 mass, that is m2g. This is the two force acting on this two objects, and let's say this angle is theta 1 and this angle is theta 2. Okay, now we will apply the D'Alembert's principle in this particular system. So Fia minus Pi dot delta Ri is equals to 0. Now for this system, for this particular system, there is only the only force that is acting is actually this m1g and m2g. There is no other force acting on the system. So we will that Pi dot, it will be 0 for this system, and the equation is only Fia dot dri is equals to 0. These are vectors. Yeah. Okay, now this dri, that is the virtual displacement. So let us say that for this m1, the virtual displacement is delta r1, and for this m2, the virtual displacement is delta r2. Okay, and as the string is incompressible, that means the magnitude of delta r1 is equals to the magnitude of delta r2. Let's say that is delta r. Okay, now we will put all this in this D'Alembert's principle. So that is Fi external dot delta Ri is equals to 0. Now Fi for the mass 1, for this m1 mass, that is m1g dot delta r1 plus m2g, that is for mass 2, dot delta r2 is equals to 0. Now this, if this angle is theta, so the angle between m1g and this delta r1 is actually 90 plus theta, 90 plus theta 1. Okay, so m1g, and delta r1 and delta r2 is equal to delta r. So delta r cos of 90 plus theta plus m2g delta r, this is cos 90 minus theta 2, sorry, this is theta 1. So how this 90 plus theta 1 and 90 minus theta 1 is coming? So if this angle is theta, then this angle will be 90 plus 90 degree plus theta 1, and for this mass 2 the angle will be 90 minus theta 2. Okay, so that will give you minus m1g sine of theta 1 plus m2g sine of theta 2 delta r is equals to 0. Now this delta r is arbitrary and it cannot be 0. So delta r not equal to 0, and we can write minus m1g sine theta 1 plus m2g sine theta 2 is equals to 0. That means m1g sine theta 1 equals to m2g sine theta 2. Okay, so for a system which is like this triangular table type system, so for the stable equilibrium the actual equation should be m1g sine theta 1 equals to m2g sine theta 2, which is coming from the D'Alembert's principle itself. Yes. Okay, so m1g is acting towards this direction, right, and delta r1 is in this direction. So this, the angle between this force and this force is actually, this is 90 degree and it is theta 1 according to the picture, right. So the component of this m1g along this theta 1 direction would be m1g cos of this total angle, which is 90 plus theta 1, right. Yes. Yes. No, that we are taking. So if you take this delta r1 as this direction, then your delta r2 will be in this direction, right, because this that will be opposite direction, delta r1 and delta r2. Now your question is right, why m1g is acting downwards, then how can the dr1 in the upside? So that is possible if your m2 is greater than m1, then the total system will slide towards the m2, right. In that case, yeah, m2 will go downward and m1 go will upward, and the opposite case will happen if your m1 greater than m2. Yeah, that's why. Yeah, yes, of course, and you can do the same problem with taking delta r1 this direction and delta r2 in the opposite direction. That will give you the same result, because in that, yes, yes. So if your masses are equal, then there will be no displacement, delta r will be 0 in that case, so that will be static. Yeah. Okay, so this is the very common, you already have used this condition for the stable equilibrium. I think this is the condition that is coming from the D'Alembert's principle also. Okay, now let us go to another example, that is called Atwood machine. Yeah. Atwood machine. So what is an Atwood machine? It is like a pulley type system. Okay, so suppose here is m1g mass and this is the m2g mass. This pulley is massless, we are assuming that, and the gravity is acting along the z direction. So also there is no constant, I mean, for in the D'Alembert's principle there will be no constant force, only the external applied force will be there. So that is Fi. I am not writing that A again. Fi means applied, just remember that, and dr is equals to 0. Now in this case, let us take that displacement of this m1g mass along the downward direction, which is delta r1. So, and obviously if it is downward, then it will go upward with displacement del r2. Okay, so our gravitational force is actually acting along minus z direction, delta r1 acting along plus z direction, and delta r2 sorry, this is along minus z direction, and delta r2 acting along plus z direction. Okay, now so if we write this equation in the open form, it will be m1g minus m1a1, where a1 is the acceleration. So we have assumed that for m1g mass the acceleration is a, and as the sting is incompressible, the same acceleration we this is for a1, and for the mass 2 the acceleration is a2. The acceleration will not be same as the mass are not same. So the total equation will be like this: 2a2 dot delta r2 equals to 0. Okay, now as you see, delta r1 is along minus z direction, so this will be m1g, when g is in the minus z direction, delta r1 is delta r1 z cap minus m1 a1, where we have taken that a1 is also along the positive z direction. Okay, yeah, okay, now ma, so this pi is the force which is the system experiencing after applying the force of Fi, right? So this pi is the acceleration of the system, so it can be divided into two. One is for the mass 1 and another is for mass 2. Okay, so this and this z is the minus z direction. We are taking the downward z as the minus z. You can take it positive z also, that will not matter, that will give you the same result. So here a1z is also downward, that means minus z direction, and delta r is minus delta r1z. Similarly, the second equation, I think you can understand, this m1g is this term and multiplied with this dr1. Okay, similarly m2g, so for m2 the acceleration is upward, capital Z, dot delta r2 z minus m2a2 capital Z delta r2 z cap, that is equal to 0. Okay, now now if you do the calculate, this negative and negative will be positive, this negative also will be positive, so the result will be m1 minus m2 g minus m1 plus m2 a m2 a, yes, and as this sting is also incompressible, so delta r1 will be minus of delta r2, which you can write as delta r also. So whatever, that will be delta r is equals to 0, and as this is an arbitrary delta r, we can that is not equal to 0, that means the term in the bracket is 0, so that will be a. Another thing, yes, another thing, here I have written only a, so your question is what is a. So a is actually a1, which is this acceleration acting on the mass 1 along the minus z direction. So so with in value this will be equals to a2, as the string is incompressible. So I was sorry, I was a little bit confused here. I told that a1 is not equal to a2. So actually a1 is equals to a2 as it is not incompressible. So the value of the acceleration will be same and it can be written as only a. So instead of a2 and a1 we have written only a as it is equal. So a is equals to m1 minus m2 by m1 plus m2 times g. Okay. Okay, so I will tell you again in details. So this was our so this was our D'Alembert's principle. It was our system. m1g is the mass here and m2g is the mass here. So we are assuming that m1g mass, that mass m1 mass is going downwards. Okay, that's why this acceleration a1 is in the negative z direction, and as it is going downwards, the m2 mass that will go upward. So that acceleration is along the positive z direction, and the displacement of the two mass will be dr1 and dr2, where dr1 is the just negative of the dr2 and the value wise they are equal. Okay, and then we are writing our D'Alembert's principle in an open form, that is for the two different mass. So for this is for m1 and this is for m2. Then we have taken our dot product accordingly, as we have chosen our forces, whether it is plus z direction or minus z direction. Then if we put all those forces and we do the dot product accordingly with plus z and minus z direction, we will reach to this particular equation, where the a1 a2 is equals to capital A and dr1, all these are all values. Okay, I mean, see, this dr and this a are all values, not direction. So this will be the equation, and a and this dr is arbitrary, that's why we can take it out from the equation, and your acceleration will be this a. Now this is now, as for our m1 mass, we have taken for m1 mass we have taken our acceleration along minus z direction. So the vector value of the acceleration will be like m2g. Okay, and for the m2 it will be just opposite, because in that case g will be directed, a will be directed in the upward direction. So this is the actual acceleration of the two mass system that is hanging from a pulley. This is the acceleration. Now from this you can also see, if m1 greater than m2, then this value, the acceleration value, is positive. So this when this mass is greater than this m2 mass, the acceleration will be along the negative z direction. Okay, so why negative z direction? Because this z is acting along the minus z direction, so a will also act along the minus z direction. And if m2 greater than m1, then there will be a negative sign just before this expression, and as so, okay, for this case acceleration will be minus m1 minus m2 by m1 plus m2 and z. And as z is always acting along the minus z direction, so minus minus it will be positive direction, positive z. Yeah, yeah. Yes, for this particular system, right? Yes, it is depends on the mass, because whether your acceleration would be in I mean, consider this m1, so whether your acceleration would be downwards with respect to m1 or upward with respect to m1, that will depend on the mass of the m2 m1 and m2. So that I am trying to say, if m1 is greater than m2, then this value is positive, right? So this value is positive, and g always acting along the minus z direction. That means your acceleration would be always in the negative z direction, because this is positive and this is minus z, if m1 greater than m2. okay, as it is a incompressible string, then that's why there will be no I mean stretch or compress of the string. That's why the acceleration will be same. If the string is not incompressible, then it will not be same. It is, yeah, it is same as this previous example. As the I mean we have taken the incompressible string assumption for the sake of simplicity. If that is not incompressible, that will be much more difficult. Yeah, okay. Okay, so similarly, if m2 is greater than m1, then this term will give you a negative sign, and there is already a negative sign in the z direction. I mean the gravitational force, that will make you a positive sign. So that will, the acceleration will act as positive z direction. Okay. Okay. Now we will do another example of simple pendulum. Okay, so simple pendulum, it is a pendulum, let's see, theta, and this length is L. So okay, now the same thing, Fi applied minus Pi dot delta Ri is equals to 0. Now let us say the force along x direction as Fx and force along y direction as Fy. Okay, so this D'Alembert's principle will take a form like this: mx double dot delta x plus okay, as it is vertically downward, instead of y, let us say it as z direction. Okay, so fz minus mz double dot delta z equals to 0. So mx double dot is the acceleration along the x direction, and z double dot is acceleration along z direction. Okay, now there are some constant in this particular system. So this length of the pendulum, and suppose everything is massless, there is no mass for simplicity. So this L square, length square, is actually x square plus z square. Right? This length of the pendulum, if it is z direction and it is x direction. Okay, so if we differentiate, 2x dx plus 2z dz equals to 0, that means x dx plus z dz equals to 0. And as we are focusing on the virtual displacement, instead of dx we will it is delta x to denote it different from the actual displacement to virtual displacement. So this is the constant which is there in the system. Now okay, now we are assuming that there is only gravity that is acting on the system, and that is along the minus z direction. So yes, so there is no I mean force in the x direction. There is no applied force in the x direction, only the applied force is the gravity which is acting on the downward direction, z direction. So Fx is 0 for this particular system. So that means mx double dot delta x plus Fz, that is the z direction force, and mz double dot delta z equals to 0. Now if we take similarly the gravity is acting along the minus z direction and put it in the equation, then it will take the form of like this: mg plus z double dot delta z equals to 0. So you can do that, just take the fz along minus z direction and put that in this particular equation and do the dot product accordingly. So there will be dot between these terms. So you will get a sorry, I have missed the signs. Yeah, so you will get expression like this. Then we will put the constant which we got here in this equation. So that will be mx double dot delta, yeah, m we can eliminate, so g plus z double dot delta z by delta x equals to 0. Now what is the delta x by delta z? That is minus z by x, right? Delta x by delta z is minus z by x, that means x double dot plus z, so it will be x by z minus x by z, that's why we will put it minus, equals to 0. So this is the equation of the pendulum, where it is only affected by the gravitational force and not any other forces. Now now if now if your system, the value of theta is very small, then we can write this z, uh, we can approximate this z as the L, because if your theta is very small and the bob is here, so there will be not much difference between this length and this length. So this is just an approximation for small oscillation that you will see later in your course also. So in that case the z will be only L, and not only L, if we take the vector length as a vector, then the z will be minus L actually, because it is the minus z direction. I am always taking the minus z direction along the downward direction. Okay, though I have written it z, consider is the minus z direction. So that's why in that case the equation will be g by L x is equals to 0. This is a very known equation for the small oscillation that you will see in your future. And in that case, as the amplitude, as the angle theta is very small, yes, not sorry, I could not hear you clearly. What I have written in the box? Okay, now why? Because but in my screen it is visible, so okay. So from the next day I will try with the portrait mode. It is in landscape mode, that's why the space is not that much, so that is my problem. Now I think you can see the whole thing, right? Okay, so this is the whole problem. So it is the equation for small oscillation. For small oscillation there is also another assumption is there, that the z double dot, which is here in the original equation, that is 0. That's why here is no z double dot equation. So I will not go details into it, you will see it later. So consider this equation. This is the equation of the simple pendulum, which is only affected by the gravity and no other external forces are there. So these are the 3 examples of D'Alembert's principle. So you can apply this in various other problems, and I would like to ask you to do some problems on this particular principle, simple problems, not complicated ones. So you can do that. Sorry. Okay. Now another interesting thing we will do, that is, I think you have done Sir's class where he have calculated the kinetic energy. T is actually half mi ri dot square summation over I. Now if you, as your ri's are a function of all qi's, so you can write this ri differentiation, ri dot means dr by dt, in terms of this qj. So sir has done this, I have seen. So I will just write what it will give you. Just if you put the ri dot in terms of q, So that will give you del Ri del Qj dot del Ri del T dot product with the same thing, but here we will not use J, we will use L. The summation over I, J and L. Now if you do it, you will get this expression AJL Qj dot QL dot plus AJ Qj dot plus A. So this is the same thing. Sir have written that as T0. This is the linear term T1 and this is the quadratic term T2. So T can be expressed as T0 plus T1 plus T2. Okay, and here also the exponent is like this, Mi delta Ri del Qj, this is I, you can go through those lectures and you will see the same thing there also. Maybe I have used the notation or defined, I mean IJKL, that is up to you. Okay, so this is the exponents, these exponents, and this is the exponent. Now using this prescription, I mean this procedure, we will try to calculate the kinetic energy of a particle which is not acted by any force and it is in the Cartesian coordinate. That is the simple particle problem. Okay, using this method. Now for a particle, free particle in 3D Cartesian. Okay, now for that our generalized coordinate q1, q2 and q3 are x, just the x, y and z. Okay, and r, which is the position vector, that can be written as y cap plus z cap, right? Sorry. Okay, and we are assuming that r is not a function of t. Okay, that's why del r del t is equals to 0. So if r is this, then delta r we can write as this. Okay, okay, now as you know, this xyz system, xyz system, so this x, y and z are orthogonal to each other, right? That's why if you do delta r by delta x dot delta r by delta y, it will give you x cap dot y cap, that is 0. So this tells you that our system is orthogonal. Okay, now why I have written that? Because when you want to calculate this AJL, that is delta Ri del Qj delta Ri del QL. That means if you want to calculate AXY, I am not writing that mi thing, so proportional to this is delta r by delta x dot delta r by delta y, right? But as you can see, delta r delta x dot delta r delta y is on 0. That means AXY or AYZ or AXZ, all those terms are 0. Only the non-zero term will be AXX, AYY and AZZ. Okay, so AJL we have calculated, and it, as the system does not depends on the time explicitly, that means the A value and that AJ value will be 0. It is also it has also been shown in the sir's lecture. So the kinetic energy will only be a quadratic function of the velocity. So there will be no linear term and no zeroth other term. So t0 t1 is 0. Now so what will be the t? it will be aii q I dot square, right? Because as I told you, all aij, that means x y y z and x z are 0, only the x x y y and z z component will be there. So x x x q x dot square q z dot square. Okay, so okay, as I have used 1 2 and 3, let it write as 1 2 and 3. Okay, so this is now what is the a11? A11 is actually delta r delta x by delta dot delta r delta x, that is x dot x. Okay, that is 1. Similarly a22 and a33. So the t will be, if we put the a1, oh, this a1 is proportional to, because there is also a half m term that I have not written, so this half m term will be multiplied with all this, so that is half m x dot square y dot square plus z dot square. So you can see we are getting the same value which we generally write t in terms of x dot y dot and z dot for a free particle in a simple system. So it is nothing but I have just tried to calculate the kinetic energy in terms of this a11, a22 and a33 to give you an idea about this particular method. Okay, so any questions in this problem? Okay, now we will do another thing, same thing, I mean we will calculate the kinetic energy, but it is in polar coordinates. So you will see there is a little change between the Cartesian coordinate and polar coordinate, and that's why I wanted to do it, to give you the idea. So suppose this is y, this is x, and this angle is phi, and this is the position of the particle. Now x can be written as r cos phi and y can be written as r sin phi. So x dot is r dot cos phi minus r sin phi, phi dot, you will get this by differentiating. I am not writing all those steps. So r cos phi, not theta, phi, phi cap. Now general kinetic energy will give you, if we don't do in that aij or jk form, so it will be, as you know, x dot square plus y dot square. So if you put, that will be r dot square plus r phi dot square. Okay, so we will try to evaluate this exact expression using that this method, which is that AJ, LAJ and A method. I mean, by this method we will calculate the same thing and we will see that those two results are exactly similar. So this you can say as method 1 and the method 2. So the position vector is x cap cos r. So r cos phi x cap plus r sin phi y cap. So that you can see it. Okay, now delta r is equals to r cap dr plus phi cap r d phi. So you may find it a little bit complex how I can write that. So this is coming from the change of coordinates. If you have done the change between Cartesian and polar coordinate, then you can see that when we will write that dr from the r, so actually what happens from r to dr, there always comes a scale factor, that is h dr plus h2 phi cap d phi. Now phi cap d phi. I don't know whether you know it or not. So if you calculate this h cap, this various factors, then you can find what will be the corresponding scale factor with the d phi component. So this what I wanted to tell you. So for a simple system, this h1 will come from dx dr square plus dx d sorry dy dr square. So if you do this, you will find that it will be cos square phi plus sin square phi is equals to 1. So h1 is equals to 1, that's why we have not written anything, but 1 is here in this with this dr component. But when you are calculating the scale factor with this d phi component, that will be same. Oh yes, but dx, then you have to do the differentiation with the phi component. Okay, so this is how the scale factors are calculated. So if you calculate, you will get so x and y, this x and r in terms of r and phi, you know, exactly these two. So I am differentiating this x and y with respect to phi and r, when which one I required. So this will give you r sin phi square plus r cos phi square. Oh, and there sorry, extremely sorry, there will be a half. So here also there will be a half, and this will give you the r. So your scale factor corresponding to the phi coordinate is actually r, that's why this r is here, the scale factor. So this is how the change of coordinate you must do, and that's why there is a, that's why you can see there will be a change in the in the kinetic energy, because in the Cartesian system it was simply x dot square plus y dot square, for but in the polar it is not simply r dot square or phi dot square, there is an extra r term. So this r terms is actually coming from the scale factor calculation, or what I have shown you. So now let us go to the problem. So our dr we have calculated as r cap dr plus phi cap r d phi, right, d phi, sorry. Now in this system also it is not a function of t, that is del r del t 0, and only the arr, a phi phi and arr and a phi phi component will be only there. So t is equals to arr r dot square a phi 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 dot square. So there will no ar phi, sorry, a phi r, all these terms will be 0. Now arr is actually half m del r by del r dot del r del r. So if you do it, you will get r cap dot r cap, that is half m, and a phi phi will give you half m phi cap r dot phi cap r, that's why it will give you half m r square. Now if you put these two in this expression, that will give you half m r dot square plus r square phi dot square, which is exactly same as this expression. So the main change will come due to this scale factor, this r, right. Okay, now this was the second thing. Okay, now that's why you have seen when for the scale factor thing, this extra r thing, when you have expressed your generalized generalized force. Okay, so for cylindrical coordinate there will be another dimension, that is z, right? No, not rho. I mean rho and r is same, not yeah, so you can write at r or rho, but the I mean convention is rho, whatever. So for that case it will be rho dot square plus rho square phi dot square, and there will be an extra term of z dot square. Okay, for cylindrical. because if you calculate the scale factor corresponding to z direction, that is h3, you will get it also as 1. Okay, so that's why there is no extra term like this r or this rho. The scale factor associated with rho and z will be 1 for cylindrical coordinate. So I will it will be good if you can go through this various change of transformation and the scale factor, all things in your, I mean, in every standard book you can find it. So it is very important for your course. Okay. Now what I was going to tell, so in one class of SIR you have must seen that the generalized force for polar coordinate, that is delta r by delta r, it you have seen as qr is actually the fr force, no problem in this radial direction. But when SIR have calculated the phi direction or the theta direction, you can find there is extra r component. So it is not only f phi, it is r of f phi. The same thing is happening there also. This r is coming from the scale factor which I have shown. So that's why the extra r term is there in the phi component. It is r f phi instead of only f phi. Okay. Okay. Now, okay. Now what is the time? Okay, very quickly we will go through some problems with the Lagrangian equation. Okay, so as you know, Lagrange equation is this, where q1 are the generalized coordinate and L is actually t minus v. Okay, for if there is no there is no force, external force, it is only true when there is no external force, otherwise you have to write it as this way. So I have not written those I dt dqi is equals to qi, where qi is the generalized force, right? Now let us do a very simple problem, that is a system which is connected with a spring and there is a mass. Okay, so this system, and it is on a surface, which is frictionless, so there is no friction. It can move only this direction and in this direction. So in this problem we will use the Lagrange, and there is no other force, only the there is no other force, and as it is not the plane is not with friction, I mean it is a frictionless plane, that's why there is no external force here. So okay, now we will first calculate the L, which is T minus V. So V, which is the potential energy, is actually minus F dot dr. Here F, the force, is actually proportional to Kx, where K is the spring constant, and as you know this force always acts opposite to the direction of the displacement, that's why there will be a minus. So F is actually minus Kx, right? So now minus Kx, and the dr is actually dx, there is no other movement except the dx direction, so it will give you the half kx square if you integrate it from 0 to x, right? Half kx, this is the v, and the t is very simple for this simplest system, it is mx dot square. So L is actually half mx dot square minus half kx square. Okay, now we will use the Lagrange equation, that is delta del x is actually minus kx, and delta L del x dot is mx dot. So the equation will be d dt of delta L del x dot, that is mx dot, minus del L del x. So minus minus, it will, I mean there is also a minus, so mx double dot plus kx is equals to 0. This is the equation of this particular system. Okay, this is the equation of motion of this particular system. Okay, so it was a very simple problem. Now Okay, another interesting but simple problem we will do, that is, let me see, yeah, let us do another example which is of a simple pendulum, like the like I have done this that before. Okay. So this is the simple pendulum. Let it be theta and the direction is L, and all the and mass of the bob is m. Now, okay, and we are taking the L and theta as the generalized coordinate, whereas the x and y are the Cartesian coordinate. So x is equals to L sine theta, y is equal to L cos theta. Now x dot is equals to L cos theta, theta dot, y dot minus L sine theta, theta dot. Okay, now kinetic energy T is half m x dot square plus y dot square. So half m, if you put that x dot y dot, it will give you the L square theta dot square, because cos square theta plus sin square theta will be 1. Okay, and the potential energy V is minus mgy. Why minus? Because we have taken minus mgy or mgz, whatever you can say. Actually we are taking this direction as minus y direction, this downward gravitational force. You can take it as z also, that doesn't matter. So L will be half m L square theta dot square minus mgy. Now as y is L cos theta, okay, so if you put it here, minus mg L cos theta, okay, that means half m L square theta dot square minus minus plus mg L cos theta. Now let us use that Lagrange formula. For there will be two equation, one is for theta dot and one is for r. Okay, so here will be only one equation, because here the generalized coordinate is theta only, because L is constant. That's why your generalized coordinate is only one, that is theta. And you can see also in L and V, in expression of T and V, there is only theta dot, there is no L dot, as L is the fixed direction. So now if you put del L del theta dot, what we will get, half m L square 2 theta dot, yes, and del L del theta will give you mg L cos theta is minus sin theta, so that is plus. So the equation will be m L ddt is there, m L square theta dot plus mg L sin theta is equals to 0. So you can remove the m also, and as L do not depend on T, this term will give you theta double dot plus g by L. So I have taken the L square just below this mgl sin theta, and one L will be cancelled, sin theta equals to 0, theta double dot plus g by L sin theta is equals to 0. This is the equation of the simple pendulum, which is coming from the Lagrangian equation. So this theta double dot plus g by L sin theta equals to 0, this we have also calculated using the D'Alembert's principle. Here you can see, but here we have not written it in terms of x theta, here we have written it in terms of x double dot, but the equations are the same for the two method. Okay, so these are some simple problem on the Lagrangian method. Now it's already 8, now we can go to the assignment problems, and in the next class I will do some problems on systems which are I mean system which have some external force. Here all this system there was no external force, that's why we can write it in terms of L, but when there is external force we have to write it in terms of T. That one example I will do in the next class, and we will do some examples of the Hamiltonian principle also. Okay, I will try to do that. I plan to do it today, but it took some time, and I will briefly tell about the homogeneity of space and the conservation of linear momentum, all those things. Now let us go to the assignments. Okay, so let me see. So this assignment was very easy. Yeah. So the first problem was that how many degrees of freedom does a diatomic molecule have? So diatomic molecule means there is two different bob of mass, you can say, and in a 3D plane, and there is no relation between them. I mean, they have not mentioned if there is any relation. If they told there is any relation, that will be some different things, but as they are independent, so x1 y1 z1 and x2 y2 z2, this 3 plus 3, this 6 coordinate is required to specify the position of these two independent atom. That's why the degrees of freedom for this case is actually 6. But suppose if there is some relation, there is some solid rod type of connection is there between these two particles, then there will not be 6 independent coordinate, because one position. Yeah, sorry. Yes, 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 whatever the bonding between them, then the degrees of freedom will be less than the than 6. Yeah, 5, exactly 5. Yeah. So but in our case there is no given relation, that's why the number of degrees of freedom is 6 here. Okay. Now second was a very easy questions, del qi del qj. You all know that the result is delta ij, because only those values will survive which is for which I and j are equals to same, right? Okay. Now another thing was half m rho dot square plus rho square alpha dot square plus half m j square, and the question asked which of the following is not a cyclic coordinate. So you know, for cyclic coordinate the condition is delta L delta Q is equals to 0. If this satisfies, then that is the cyclic coordinate. So in our system, just a second, have I taken the same question? Yes. So in our Lagrangian, delta L delta rho is not equals to 0. Oh, it was asked which is not a cyclic coordinate, I think. Yeah, which is not a cyclic, whatever. So delta L delta rho not equals to 0, because rho dependency is here, but delta L delta alpha is equals to 0, because in this whole expression there is no alpha term, only the alpha dot term is there. That's why delta L delta alpha is 0. So that means your alpha is cyclic but rho is non-cyclic. This is the condition for the cyclic coordinate. So in the whenever you see a Lagrangian, just try to find out which I mean the coordinate is there with the dot but not itself. I mean here a dot is there but no a is there, that's why a is the alpha is the cyclic coordinate. Also delta L delta yes. So another thing, rho alpha, yes. So this was that question, question number 3. Now question number 4. Okay, question number 4 says a L is given r dot square r square theta dot square plus g m m by r. It is given, and the value of the conserved momentum. Okay, this is value of the conserved momentum. Now the question is which are the conserved quantity. So conserved quantities are those which are associated with the cyclic coordinate, right? Because if you know d dt of del L delta alpha dot minus del L del alpha equals to 0, and as alpha is cyclic, this is already 0. That means d dt of delta L delta alpha dot equals to 0, and this delta L del alpha dot is actually the momentum along the alpha direction. So time derivative of the momentum is 0, that means the momentum is conserved. The same thing will be here. So at first you have to find which is the cyclic coordinate. So in this equation there is theta dot but no term with theta only, that means theta is the cyclic coordinate here. Now just put that just use that Lagrangian equation, sorry, theta equals to 0, and put L in put this expression in place of L, and you will find that which is the conserved momentum, and you will find that conserved momentum will be mr square theta dot. I think that will be constant. I am not doing that. You can just put the L in this expression and you will find this is the constant. Now in the last question there was a Lagrangian given, that is half m q1 dot square plus q2 dot square minus half kl square q2 minus q1 whole square, and you q2, and you have to now change that. It is given in the question that just replace q1 by this and q2 by this, q1 minus q2 by root 2. So and it is just some algebraic calculation. Just calculate the q1 dot, which will be a function of q1 dot and q2 dot, similarly q2. Then if you just put that q1 dot and q2 dot in this expression, you will get the result. So I have already done that. I will not do again. I will just show you. So yeah, so here you can see this, sorry, so this was given in the equation, and q1 q2, then you have to change the q1 dot and you have to calculate the q1 dot and q2 dot, and if you put that q1 dot and q2 dot in this original equation, you will find that the Lagrangian will be like this, where the q1 capital Q1 dot term will be there, q2 dot will be there, and q2 will be there. So there is no terms which included q1 only, not the q1 dot. So that means that q1 is cyclic, because in that case delta del q1, sorry, delta del q1 will be 0, and this is the condition of the cyclic coordinates. So q1 will be the cyclic coordinate for this particular Lagrangian, capital Q1. Okay, so this was the assignment question, and you can just put that, and it is not a big deal. Okay, so you have, if you have any other question, you can ask, and if you have not understood anything from today's problems, you can also tell. Lagrangian method you can use for every problems. I mean, I don't know if there is any particular limitation or not, but you have to be careful whether what type of the forces are associated with that particular problem. So it is, if it is not a conservative force, then you cannot write that L equals to T minus B, then you have to calculate the T and generalized force separately. So this type of limitations are there, but right now I don't think, cannot recall if there is any limitation, but I will check if there is any. Without verifying, it will not be good to give any answer. Yes. Okay. So try to do some Hamiltonian related problem also if you can. Those are very simple problems, and you can find many problems in books also. But I will do 1 or 2 problems in the next day. Okay. Okay, then if you don't have any question, we can end today, and we will meet next week. Okay, thank you for joining.